Okay, so in this video we're going to talk about another way to find the volume of a integral being rotated around an axis. So we talked in the last two videos ago about the washer method. I don't think I said the name of it, but that's what it was when there was that hole in the middle and you rotated around because you're thinking of it like circles. Now I don't know if you guys did this in your calculus class, but you would notice that if, let's say, we had that same one that we did in that video, which I believe was this one. It looks something like this. We had that value right there. If you were asked to rotate this around not the x-axis but the y-axis, and you wanted it to look something like that, and get that volume, you couldn't do dx. You would actually have to do it in dy. You would first have to find these equations in terms of dy, and to do that you would basically have to flip it sideways and think, well, if y equals square root of x, then x equals y squared, and you would have to use that equation instead and kind of look at it sideways. Your calculus teacher should explain that to you. However, with this new method I'm about to teach you, you're not going to have to do that any longer. So let's give us a more interesting equation. How about like sine of x or something? So it would look like that, and then it would continue on. But we're only going to look at this much of it. And let's say your teacher asked you to rotate this around the y-axis. So if it was the x-axis, then you would just do these little circles that I taught you and do pi and sine of x squared from 0 to pi. However, I want you to do y-axis. A very easy way that you can do this is using something called the shell. I think this one's called the shell method. Or something like that. That's what you would end up with. So here's how we're going to do this. Instead of doing circles, we're actually going to be using tons and tons of cylinders. Because we're still going to be taking these vertical rectangles that we were taking before, which used to be the radius of a circle, but if you rotated this around the y-axis, you would actually get a cylinder. Something like that. A cylinder with a big hole in the middle. And so what the shell method is saying is it's saying that you're going to use an infinite amount of these cylinders until you have the right area, and you can use an integral to do that. So what we're going to do is I'm going to give you the equation. I'm going to explain where it comes from. Just make sure I'm writing this down right. The volume of this equals the integral of, from a to b, if this is a and this is b, of 2 pi r times the height, and then there's a thickness factor to it, and I'll explain what th means in a second. So the 2 pi r comes from circumference. If you were to take what the x value was, and in this case it'd be something like this right here, which will become infinitely small, and you wanted to find out what the circumference was, that'd be 2 pi r. Then you're going to multiply it times the height to be able to get that cylinder, and that way you get the cylinder with the hole in the middle. Then there's a thickness factor to it, and this is kind of like before. This will be the dx, dy, or whatever. This is kind of giving it the unlimited thicknesses to be able to get the precise volume. So for this exact one, we're going to take the integral from 0 to pi of 2 pi times the radius. Now this radius is a little different, where this isn't going to be like before. Most of the time, when you are rotating it around the y-axis, this is going to simply just be x. However, there are times it won't be. If the question is asking, it gives you the same scenario and says it wants you to spin it around x equals like -2, we'll just think that instead of the radius being the distance of x, it'll be the distance of x plus 2 more. So in that case, it'd be x plus 2. But usually, especially if you're rotating around the y-axis, it'll just be x. Also, I do want to mention that because one of the rules of integrals is you can pull out constants, you can actually put a 2 pi out here and then put the x there, but I'm going to just leave it all in because it fits the equation I gave you, so it would be 2 pi times x times the height, and the height would be the equation, so this would be sine x. And then the thickness would be whatever variable you're using, so it would be dx. And there is a way that you can find the volume when being rotated around an axis that is parallel to the rectangles that you're making for the integral.